Now the second part, this part is different as the bar element, so which is the element equivalent node forces, element equivalent node forces. So we said for the beam element is different, because for the beam element, the node force, the external force can be on the node or not on the node. So, but when if you notice the stiffness equation, we have the external node force matrix, and the external node force matrix is only consider the force at the node. So which means if you have a external force which is not on the node, you are not able to consider this force, external force, in the stiffness matrix. So if you don't consider this into the stiffness matrix, which means you are not taking into account the effect of this force. So therefore, we need to do this. We need to transfer this force, the non-node force, into the node force. So we get the equivalent node force for those unknown force, and then we can take into account the effect of those kind of force. So this is a key or an important procedure. That's why we do the element equivalent node forces. So the aim, as I said, is to transfer all the non-node force into the node force in order to consider its effect, in order to put it into the stiffness matrix. So the problem we have here, so we have the concentrate force. We have the concentrate force Px and Py and the moment, and we have, this is our element. They have two nodes, node I and node J. Okay, so we can know those concentrated forces, they are not on the node. They are not on the node. So then we need to work out the equivalent node forces for those external forces, and then we can use the stiffness equation to take into account the effect of those force. So here we assume, so let's have a look at the procedure, how we work out the equivalent node forces. So we assume the equivalent node forces are those. So we transfer those to the equivalent node forces at the two nodes. Okay, the Fxi, Fxj, Fyi, Fyj, Mi, Mj. Okay, is the equivalent node forces, and then we use the virtual energy method to work out relationship. So actually we want to, what's the relationship between them? So if we can set up the relationship, which means we use those variables to express those. So we want to set up the relationship between them. And how to set up the relationship? We want to use the virtual displacement method. Okay, so for this system, if we give a virtual displacement, and this should be still in the equilibrium state, so, and then we can set up the corresponding relationship. So we give the virtual displacement at the node. This is I, the virtual displacement at node I. This is the virtual displacement at node J, and then the virtual displacement will also give the virtual displacement at this node. Okay, U0, V0, theta 0, and then what we do here, we know the relationship between those virtual displacement. Okay, because this is using the concept of the interpolation, and this is the shape function. It's the shape function of the beam elements. So which means if we already know the concept. So if we know here. So if we know the displacement at the node, and then we can use the displacement field function of this beam element to work out the displacement at any point inside the element. Okay, this is our what we write it down when we work out the FE procedure. Okay, and in order to know, so we know once we know the shape function of the beam element, then the displacement field function is already known. So for a given beam, if we know the parameter, if we know the Young's modulus, if we know the geometry, and then the shape function is already given. So those are the known parameters. And then, so which means we can easily set up the relationship between them. This can be easily solved. So then we continue with the procedure. So we have the relationship between the node displacement and the displacement at the external concentrated force. Okay, and this is the shape function. Okay, this is the shape function for the beam. The shape function for the beam, and so this is the we already know this. This is from the bar element, the shape function for in the x direction. This is the shape function for the general beam. Okay, then this is the relationship between the displacement at the concentrated force and the displacement for the nodes. Okay, and then these are the shape function. These are the shape function for the general beam, and in general case it's like this. Okay. Then we can work out the virtual work. So first, the virtual work at the node is the force times the displacement. Okay, this is the general concept. And then the virtual work on the non-node force. So the virtual work is done by the concentrate external force, and then it equals to the force times the displacement. Okay, and the displacement we can write in terms of this, the node force, the node displacement times the shape function. And then we set this equilibrium system, so which means the virtual work at the node and should equal to the virtual work done by the non-node forces. So those are the two work, they equal to each other. Then we set up this equation. So which means here WD equals to WP. Then we can set up this equation, and we do the mathematics. We can further do the mathematics to eliminate those, and then what we get is the relationship between the node force and the external force. Okay, and then the relationship between them is linked also by the shape function of the element. So that's why we say the shape function is very important. Because we can see here is link it will be used to work out the equivalent node forces. Okay. So this is the general equation. Okay, this is the general equation, which means no matter what form is your external force, you can use this equation for the distributed force, concentrated force, or other terms of the force. But here we use several cases to demonstrate this equation or to understand this equation. The first case is the distributed load. So we have the force. We have the force here, and then by using this equation, we can work out the force at the two nodes. So this is the equation for the in case of the distributed load. And this is you can use this equation to work out for other cases. For example, it's the simplest case is we have the concentrated force at the center of the beam, and this is offset concentrated force in the beam. And this is the distributed force in the beam. And this is the triangular distributed force on the beam. And for different cases, you can use the formula to work out the equivalent node forces. For example, we convert this force to node A and B, and we work out the equivalent cases. And here we also work out the equivalent cases. And this is for you to practice. Okay, you should try yourself to work out whether you're able to work out those parameters or not by using the formulation we gave to you. Now let's have a look one example for the beam element. Here we do it by hand, but in the FE analysis they use more elements to match the structure, so they do it automatically. But the aim, what we demonstrate, is the procedure which is used by the FE analysis. So if you know this procedure, then you know how the FE software is doing behind the software. Okay. So using the FE method to solve this problem, so we have a beam. And one end is fully fixed, and here and here is free to move in X direction. And this is we have a normally distributed force in from 2 to 3. And to do the FE analysis, first we do the discretization. So we mesh the structure into two parts. Okay, the first part and the second part. So and then we have two elements. We have three nodes, and in this case we can say we don't have the axial displacement because there's no external force in the x direction. So which means for each node we have only 2 degrees of freedom. So which are node 1 we have V1 theta 1, node 2 we have V2 theta 2. V is the deflection, and then then we can work out the displacement field matrix for the entire structure, for the whole structure. And then next we said for the difference for the beam element is we have to work out the nodal equivalent node forces, because the external force is not on the nodes. We have to transfer into the node forces, okay, to work out the equivalent node forces. So this is only applied to the element 2, okay, only applied to element 2. So for element 2, we can use the formula to work out the equivalent node forces, okay, equivalent node forces. Once we know the node forces, then the next step we work out the element stiffness matrix. For the element stiffness matrix, we just use the formula we have. So we use the formula we give to you, and then by using the Young's modulus and the dimension of the element, then you can work out the element stiffness matrix. And then the next step is we do the stiffness equation. Okay, we do the stiffness equation. And we said the original stiffness equation may be very large, so we take use of the boundary condition to reduce the dimension of the stiffness matrix, and then we can solve our unknown variable. Our unknown variable is the displacement at the nodes. Okay, and then once we solve the displacement field, and then we can use different equations to solve the other physical quantities. So here the displacement of the element 2, so deflection of element 2, and also the string or stress distribution at the element 2, we can also use the corresponding equation to solve it. Okay, Part 3 is the coordinate transformation of beam element. Coordinate transformation. Coordinate transformation is similar to the bar element. So, because here, even for the example, we only talk about the condition, the beam is aligned in the x direction. But in the real engineering problems, you will have the beam not aligned in the x direction. So you have an inclined beam, and the angle between the axis of the beam and the x will be alpha, will be an angle alpha. So in this case, we have to do the coordinate transformation in order to solve the corresponding variables, or in order to consider different beams, and that's why we have the coordinate transformation. Okay, the coordinate. So again, the aim of the coordinate transformation is to align different beams into the same system. For example, in a global coordinate system, then you can set up the stiffness equation for different beams. You can put them together, then you can solve the problems. Okay, so let's have a look. Example here. So we have the degree of freedom in the local system, and we have the degree of freedom in the global system. And then by use this graph, this figure, we can have the relationship between different variables. And then we have our transformation matrix T. So we can use the transformation matrix T to transform the node displacement matrix from the global system to the local system. Also, you can do the inverse. You can transform the displacement the node displacement matrix from the local to the global. So we can use this. This is the format or the form of the transformation matrix. And then we can rearrange our stiffness matrix. We can arrange it in a global system. In a global system, we take use of the transformation matrix. So because here bar is the Q bar is means the variable in the global system. So we have here, this is the stiffness matrix in the global system. Okay, and then the stiffness matrix in the global system equals to the stiffness in the local system times the transformation matrix. Okay, similarly, for the force in the global system equals to the force in the local system times the transformation matrix. Now we know how to transform different beams into the global system. Then we can solve a more complex scenario. For example, here for this scenario, we have 3 beams in different orientation. So for the beam 1, it's along the x direction. This will be easy to do. But for beam 2 and beam 3, there's 19 degrees to the x directions. So we need to do the transformation for 2 and 3 in order to make the variable, to align the variable into the global system. Then we can set up the stiffness matrix in the global system. So this is the parameter for the structure. We have Young's modulus of this. I'm going to have the inertial moment. We have the cross section. So again, we do the mesh. So which means we do the structural discretization. So we mesh using 3 elements. We don't use too many elements. We only use 3 elements. So, but in the real, if you solve this in the FE analysis, you can mesh with more elements, so then you get more accurate answers. So we have the 3 elements, and this defines the orientation of the element. So which means element 1 is from node 1 to node 2. This is the orientation. And element 2, we define the orientation is from 3 to 1. So this is the orientation of element 2. This is the orientation of element 1. And element 4 is this is the orientation of element 4. Okay, because we define this orientation, so the angle here is 90 degrees. Okay, so for example, if we define this orientation, and then the angle will be different, will be 270 degrees. Okay, so and then the value will be different. So it's important you define the orientation of the element. And for example, for the element 1 will be 0 degree. Okay, and for element 3 also will be 90 degree. Okay, then we continue. So this is the variable. Okay, for the whole structure. For the whole structure, this is in a global system. For the whole structure, we have the node displacement vector, and then we have to work out the equivalent node forces before we set up the stiffness matrix. Okay, let's have a look what external force we have. So we have this is our external force, and it's not on the node, it's on the beam. So we have to work out the equivalent node forces at node 1 and node 2, and we use element 1 to solve this. And this is the simple case. We have a normally distributed force. So then let's have a look how we solve this. So we work out the equivalent node forces. For normally distributed force, we have the force and we have the moment, equivalent force and equivalent moment. Then we have the external node force matrix like this, and then the reaction force matrix, and then the total node force matrix is the sum of the external node forces and the reaction force matrix. And then the stiffness matrix, as we said, we use the formula to work out the element stiffness matrix. And then we do the transformation to transform this stiffness matrix into the global system. The same we do it for element 2 and element 3. And then we can set up the global stiffness matrix for the whole structure, and then we take use of the boundary condition. Those are 0, so we can reduce the dimension of the global stiffness matrix. And then we solve these equations, and then we obtain the displacement for the nodes, variables. Okay, this is the whole procedure. So once you solve the node displacement, then you can solve the displacement, the strain and stress in the structure. Okay, the last part is the treatment of boundary condition. So we said we have two types of boundary condition. First is the displacement boundary condition and the force boundary condition. And here we want to tell you how to use some technique to quickly consider the boundary condition in the FEE analysis or in the coding. So you can, it's kind of some small techniques, some tips to put those boundary conditions into the global stiffness matrix. The first is 0 boundary condition, so which means we have the displacement at a certain area or certain node is 0. And the second case is the given displacement boundary condition. So at a certain area or certain node we have the displacement of U bar. And then we have the global stiffness equation like this, global stiffness equation. So and here is the Kij QA and PB are known, and QB and PA are unknown, are to be solved. So we introduce two methods. First is the direct method. So for example, if we know the displacement at a certain point are 0, so we get rid of the 0 elements, and then we have those. So this is a direct method. So we use this condition into the stiffness matrix. Then we have a reduced form of the equation. So this is what we used in the previous lectures when we solved the stiffness matrix for the bar element and for the beam element. So we get rid of 0 element, and then we do the inverse. Then we have the solution. And in the second case, so we have the given displacement for certain area, or so for certain nodes, and then so we have which means we know the QA. So we use the direct method. So then we can work out, okay, QBB equals PB minus KBA and U, because this is U. So from the second equation we get this, and then from this equation we do the inverse for this, and then we can solve the variable QB. So this is the direct method. So what the direct method means, we directly put those values into the matrix, and then we solve the equations. But this is not preferred in the FE coding or in any coding. We don't prefer this. Why? The reason is, you can say here, when you get rid of the 0 element, you are changing the dimension of the matrix. When you have a large matrix, and you change the dimension of the matrix, and they sometimes will cause the error. Second, so when we try to work out QB, we are doing the inverse of the matrix. And if you have the experience of coding, you will know whenever you do the inverse, it will take a long time. So we normally, for the matrix operation, we don't do the inverse. Okay, here we are doing the inverse. Okay, so here the shortcoming of this method. So because the change of the matrix, this method is not good for computer, or it's not good for computer programming. So let's say what the preferred method. So we don't prefer direct method. So we introduce two preferred methods. The first method is to set one method. So for example, if we have this boundary condition Q0, QR equals to 0, then we use the set one method. So we set QR, so corresponding QR equals to 1, and others equals to 0. So those are 0, and we set this to 0. So we can say this when we set up those, then it's equivalent to, so we do the matrix operation, this one times this one equals to this one. Okay, then we get QRR times QR bar equals to PR. Okay, and because this equals to, we know this equal, we have set up this to 1, this to 0. So which means this equation is QR bar equals to 0. So which means we set up these parameters and it's equivalent to QR equals to 0, QR bar equals to 0. So by set up those, we have considered these boundary conditions. So this method, we call it set one method. And you can know the advantage of this method. We don't change the dimension of this matrix, this big matrix. So we keep the same dimension, and then it'll be easier for the matrix operation. So this method is only applicable for QR bar equals to 0, and the advantage of this method is they keep the dimension of the original matrix easy for the computer processing. And then we have another method, we call it the multiply big number method, and this method is for this scenario. For the scenario, we have a knowing give value, we have no giving value. So how to get the equivalent condition? So consider this equation into the stiffness matrix, we set up those parameters, and so kind of these are equivalent. So we set up QR equals to alpha times KRR, where the alpha is a very big value, and we set up PR, the corresponding force, external force, PR equals to alpha times KRR U bar. Okay, and then we don't change other parameters. So we only set up these two parameters. So be careful here, alpha is a very big value, should be very big value. Very big means comparable to other parameters, it should be very big. So let's have a look. Similarly, we do the matrix operation, this one times this column, then equals to this one. So this is the mathematic. And in this equation, we said alpha is a very big value compared to other parameters. So this is very big. So which means we can ignore those terms. When we ignore those terms, we have this equation. And for this equation, we can eliminate KRR, and alpha also eliminate. Then we have QR bar equal to U bar. So kind of we have managed to consider this condition. So which means this given boundary condition equivalent, we set up those parameters. And we can see the advantage of this is also we keep the same dimension of the matrix, so it's easy for computer processing, and this only applicable to the given boundary conditions. So here we introduced those. This is not important because nowadays we have many advanced technique or many advanced algorithm to do this, and this is only for you to know. And here is the exercise, so you can practice your skills and to do this exercise. So we have a very complex case. So we have 3 beams. And these 3 beams, they are in different orientation. And here is this beam, and this is the first beam, and this is the third beam. And we have very complex scenario for the external force. So for example, here we have the normally distributed force here, and here we have triangular distributed force here, and we need to work out the equivalent force for this external force. We have to work out equivalent force for this as well. So you can try yourself to work out, to solve this structure, to find the node displacement in the structure. Okay, so this is only for your practice, so you don't need to submit. If you are interested, you can do this, and if you want to know the answer, then you can contact me, then I can give you the answer, you can check. So the reason we do those is really only for you to know or to understand the theory, and for you to be an expert in the FE analysis. But in the future, when you do the real engineering problems, or when you use the FE software, normally you don't do those hand calculation. Okay, you don't do those hand calculation, but whenever you finish the hand calculation, you will understand your analysis, the result of your analysis much better. Okay, this is the aim of this lecture. Okay, this is the end of this chapter. Okay, in the next chapter, we will